So up until this point, we've spent a lot of time talking about bonding, how bonds form, types of bonds. In Chapter 10, though, we're going to focus on what are known as intermolecular forces. And we want to be very careful and distinguish between those and bonds. So if we were to use the term intramolecular forces, that's when we're talking about bonds. And these are what determine the reactivity of molecules, among many other things. But most importantly, this is what determines reactivity. So here we're going to focus on intermolecular forces. These are forces between molecules. And these are responsible for things such as solubility, and melting point or boiling point. Now, as we get into intermolecular forces in more detail, we're going to find that temperature changes can alter these forces, and in some cases quite significantly. So why do these things matter? Well, let's look at the following. So these are a representation of a protein. And if you go on to take biochemistry, you'll learn a lot more about proteins. But when we talk about proteins, proteins have what we call 4 different levels of structures. The first level, or what we call the primary structure, is literally, this is the order that the amino acids appear in. Doesn't tell us anything about the shape of the protein, but just literally what order do the amino acids come in. Now when we say amino acids, we're referring to the 20 naturally occurring amino acids, which you can see here. And the important things to remember with amino acids is every amino acid has 2 things, or we could even broaden that and say it has more than that. But it has this carbon double bonded to oxygen and single bonded to an OH. This is what's known as a carboxylic acid group, and you can see it's present in every single protein. In addition, every protein has this NH2 group, although in the case of proline it ends up being an NH. But that NH2 group is on the same carbon as the group that we just referred to as a carboxylic acid. In organic chemistry, we call this an amine. And so that's actually where this name amino acid comes from. The third group on an amino acid is some other group. And in some cases you can see it's very, very simple, like here in alanine, it's just a single carbon. But in other amino acids, such as arginine, it's another fairly complicated group. So the reason that this matters is what happens is that this chain of amino acids that we see as the primary structure will bend and cause different types of patterns. two of the most common are what we refer to as these beta pleated sheets and an alpha helix. And this is all caused by amino acids that are not next to each other on the chain interacting and having attractions with each other. Then on top of that, we get the tertiary structure, which is further folding of the secondary shapes. And then a quaternary structure, which is the interaction of multiple proteins. But with the exception of the primary structure, all three of these secondary, tertiary, and quaternary structures are controlled by intermolecular forces. And so it's these forces between different amino acids that control the shape of the proteins, and in some cases that can control the entire function of the amino acid. Probably the best known example of this is in hemoglobin. In hemoglobin, it turns out that there's one specific amino acid that if you change that one amino acid, the hemoglobin doesn't work properly, and that's actually what causes sickle cell anemia. So before we get into some of the specifics, let's talk about states of matter. So the first question we could ask you is, how many states of matter are there? Many of you will probably answer that there's three: solid, liquid, and gas. Or some of you may recall a fourth: plasma. But those are just the normal states of matter. Turns out there's quite a few more. Now, most of these we don't really worry about. Any of these are pretty special case, very odd states of matter, and that really don't have any impact or effect on our life. So we will just kind of disregard those. But it's important to know that these things exist, and they're not quite as simple as maybe we once thought they were. Of course, here we're just going to deal with our three common ones: gas, liquid, and solid. So what are the common properties that you might associate with some of these different states of matter? Well, some of these we've talked about before. Maybe the first one is we could talk about shape. Which of these three states of matter has definite shape? Typically only a solid. We know that both liquid and gas, they can both change their shape to the shape of the container. How about volume? Well, a solid has a definite volume, and a liquid also has a definite volume. But we saw in the last chapter, and we talked about quite extensively, that gases don't have a definite volume. Again, they can conform to the shape of their container. What about flow? Well, gases usually flow very, very easily. Most liquids flow, but solids don't flow. We can compress gases, but we can't do that with liquids or solids. So that's what's happening on a macro level that we can see. What's happening on the molecular level? Well, for gases, we have highly random movement. In a liquid, there's some restriction of movement. And in a solid, the molecules are pretty much locked in place. And the reason for this is because we have very strong attraction in a solid. In a liquid, there's sort of a moderate level of attraction. This is why we have the ability to flow in liquids, because the molecules can move past each other. They're not locked in place. And in a gas, we have completely random movement because the attraction between molecules is very weak. Now, what is it that determines whether something is a gas, liquid, or solid? Well, that's where we get into the intermolecular forces. So the first thing I want to be very, very careful to say, intermolecular forces are much weaker than bonds. And when we say much weaker, how much weaker do we mean? Well, let's look at the following. Let's say we have hydrochloric acid. And we're going to look at the intermolecular forces, which we could demonstrate by going through a phase change, liquid to gas. And we can also look at the intramolecular forces, or the bond. So what would it take to convert hydrochloric acid to hydrogen plus chlorine? So for the phase change, we're going to use this term delta H. Don't worry about what this means right now. It's something we'll talk about later. Right now, we're just going to use it as a way to measure energy difference. So going from liquid to gas with hydrochloric acid requires approximately 16 kilojoules per mole. So pretty low amount of energy. And we can compare that to a bond. So breaking the actual hydrogen-chlorine bond, that requires 431 kilojoules per mole. So more than 25 times the amount of energy that we needed to just do a phase transfer. We needed more than 25 times that amount of energy to actually break the bond. So you can see based on these numbers, an intermolecular force is much, much weaker than an actual bond. But still very, very important. So what determines intermolecular forces? Well, these are based on attractions of dipoles. So we often say that IM forces are electrostatic. And again, all this word means is that it's based on the dipoles. So the stronger the dipole is, leads us to more attraction. And so those stronger dipoles, stronger intermolecular forces, will often have higher melting points and boiling points. And if you think about this, this should make a lot of sense. The more two molecules are attracted to each other, the harder it's going to be to pull them apart. Well, if it's harder to pull them apart, then pulling them apart is going to require more energy. And more energy means higher temperature. So what are some things you could think of that might have a very, very low melting point or boiling point? And what's something that might have a very high boiling point? And let's look at a couple examples, and then we'll start talking about what causes these. So how about helium? So helium is a very small molecule. It's not polar at all. It's just 2 protons, 2 neutrons, and 2 electrons. And so it has an extremely weak attraction. And we can look that up. So what's the melting point of helium? So the melting point of helium is negative 272 degrees Celsius. So just right around 1 degree Kelvin. So do you think we ever use helium in its liquid or solid form? Turns out you might be surprised. Turns out liquid helium is actually used quite extensively. So the following picture is known as an NMR, or nuclear magnetic resonance spectrometer. And a nuclear magnetic resonance spectrometer is something that we use quite extensively in organic chemistry in order to determine the structure of molecules. It turns out these only work properly, at least instruments like this, if you cool the magnet down to about 4 degrees Kelvin or so. And the way that you do that, there's actually a port right here where you fill them with liquid helium. And so that's how you keep them cold. Unfortunately, because these types of instruments are so important, we actually have a shortage of helium these days. And helium, believe it or not, has probably over the last 10 years more than tripled in price. And is getting to be very, very difficult to get. But in fact, you may not know this, but many of you at some point in your life have had some dealings with an instrument like this. Turns out nuclear magnetic resonance spectrometer, Well, if we get rid of the word nuclear on it, not only are these great for analyzing the structure of molecules, but they're great for analyzing, injuries. And so while the instrument obviously looks a lot different because an instrument like this, the sample that you put in is less than a centimeter in diameter, as opposed to an MRI instrument where you need to fit your knee in there, for example. So the instruments look drastically different, but it's the same technique. It's just they had to change the name because, of course, the word nuclear scared people. But what does nuclear refer to when we're talking about NMR? Well, really, it just refers to the nucleus of the atom. So helium would be an example of something that has an extremely low melting point or boiling point. What would have a very high one? Well, have you ever gotten salt to melt? Sodium chloride? Can you make liquid sodium chloride? You can. It just requires that you heat it up to, at least 800 degrees Celsius. So in the case of sodium chloride, the attraction between the sodium chloride molecules is extremely strong. And that very, very strong attraction results in this very high melting point.